Hello, we are Project 26091, presenting our design of an arsenic detection device production process. On the ends, we have Cameron and Crispin, environmental engineers. In the center are Tomidul and Wenhao, chemical engineers. This is our poster. It shows a brief summary of project background, design, and results. The goal of this project is to develop a paper-based sensor capable of detecting arsenic in water using silver nanoparticles. With a focus on approximately 29,000 hand wells in Murshidabad, India, the design was developed by considering the regional arsenic contamination levels and current public health standards. With these sensors, users can quickly identify arsenic-3 contamination and understand if current filtration methods are failing. This project integrates process design, engineering principles, and economic feasibility to provide a balanced, practical solution to the critical issue of safe drinking water.
Arsenic is a metalloid that is extremely dangerous when ingested, having serious long-term health effects. Some of these effects include cardiovascular damage, cancers, neurological effects, and death. Effects of arsenic are directly correlated to the amount ingested. Unfortunately, it is commonly found in groundwater worldwide, which makes it extremely hazardous for communities reliant on groundwater as their main source of drinking water. Murshidabad is one of these communities. It is a large district in the Indian state of West Bengal. It has a population of around 7.1 million, with most living below the poverty line. Additionally, it has high levels of arsenic contamination, with approximately 54% of its wells exceeding the Arsenic World Health Organization guidelines of 10 micrograms per liter. This means 4 million people are exposed to chronic levels of arsenic. Murshidabad could desperately benefit from arsenic testing, which is why it is the targeted community. There are different established methods for arsenic detection. However, they vary widely in scope and feasibility. Some methods, such as the Gutzai method, are dangerous. Other methods, including laboratory testing, are expensive. Silver nanoparticles were selected as the optimal medium of detection. Silver nanoparticles can produce a visible color change caused by interactions between arsenic and nanoparticles. They are simply synthesized and can be mass-produced for large-scale production. Additionally, they are easy to use in the field via test strips and have reliable performance, making them the most practical choice.
Foundation of our project comes from a 2019 research article by Borua, Daimari, and Biswas, published in Results in Physics. The synthesis works by chemically reducing silver nitrate using trisodium citrate, then adding polyethylene glycol to functionalize and stabilize the nanoparticles. Chemical properties of PEG place a negative charge on the silver nanoparticles, which is responsible for their stability and repulsion, preventing any agglomeration from occurring. What makes this method more powerful is the colorimetric response. When arsenic-3 is present in a sample, it interferes with the hydroxyl groups of PEG and essentially flips a switch, allowing the silver nanoparticles to agglomerate, which manifests into a colorimetric shift from yellow to blue. The nanoparticles are capable of detecting arsenic-3 down to 1 part per billion. We adopted their synthesis protocols as the basis for our own work. The reagents, reaction conditions, and functionalization approach all come directly from this paper. From there, our team built on that foundation in a few key ways. First, we scaled up the synthesis process and designed a system to spray the nanoparticle solution onto a single-use paper that a user could use to test their water directly at the tap and get a colorimetric result on the spot. We also recognize that scaling up production generates waste, so we developed a recovery process to reclaim unused silver and remove organic contaminants from the processed wastewater.
This is our this is our project workflow diagram. This BFD shows the overall process of producing arsenic texture paper. This is our process flow diagram. At the beginning, for materials are added into a reactor. The reactor is used to synthesize silver nanoparticles. After synthesis, the reactor outlet is split into a centrifuge. The centrifuge can remove too large and too small nanoparticles. After centrifugation, the water, the wastewater is sent to the wastewater tank, and the usable product is sent to the product tank. From the product tank, the nanoparticles solution is delivered to sprayers. At the same time, the waterman paper is filled in. In In the stage, the silver nanoparticles is uniformly coated on the paper surface to form the article sensor layer. Then the paper are dried and storage at 4 degrees Celsius. This is our silver recovery strategy. This section is designed to recover silver from the wastewater. In the reactor, nitric acid oxidizes the silver nanoparticles into a recoverable silver ions. After reaction completely, the outside is pumped in a filter. At the same time, NaCl is sent to the filter to act with the silver ion and form the silver chloride participate. This participation step enables the silver to be separated from the liquid surface.
Protective coating is implemented as an outer layer to hold silver nanoparticles in place on the testing strips. It is made of a combination of polyvinyl pyrrolidone and water. The primary purpose of this coating is to prevent the nanoparticles from detaching during handling, transportation, or when the sensor is exposed to water during sampling. Without this protective coating, nanoparticles could be lost, which would reduce the accuracy and the reliability of sensors. At the same time, the coating is designed to remain permeable, which allows arsenic in the water to still reach the nanoparticles to produce a color change.
For our water treatment system, we chose electrochemical oxidation for its ability to completely destroy organic contaminants with no chemical additives and no phase transfer. At the anode, water is oxidized to produce hydroxyl radicals that attack and mineralize PEG 200 and citrate. The system operates at a charge density of 30 milliamps per square centimeter with a 5-hour contact time. Our wastewater carries an initial theoretical oxygen demand of 2.3 grams of O2 per liter, which is essentially a measurement of the wastewater's organic load. It represents the amount of oxygen required to successfully oxidize an organic compound. After treatment, that drops 98% to 44 milligrams per liter, meeting regulatory discharge requirements or enabling full water to recycle.
This is our economic table where we have the total annual cost, the annual profit, and the profitable selling price that we figured out with calculation. Our economic analysis indicates that the process is financially viable at industrial scale with annual operating cost of approximately $14 million and production cost of about 45 cents per sensor. Using a 50% profit margin, the selling price is set at 67 cents, which is 62 Indian rupees per unit, generating roughly $20.94 million in annual revenue and nearly $7 million in annual profit. This pricing remains practical for Indian market through NGO and government distribution channels while supporting affordable large-scale groundwater screening. This project is considered successful because it targets a high-risk population with limited resources, addresses the urgent and widespread issue of arsenic contamination, scalable solution for thousands of wells, accessible to low-income communities, economic sustainable. Overall, while there are areas for further development, this project demonstrates a realistic, scalable, and impactful way to address arsenic contamination in drinking water. Thank you very much.